Hi there, and welcome to Mr. Morgan's Math Help for Algebra 1. We're in Unit 1 still on one variable statistics. This is Lesson 12 called Standard Deviation. Learning goal, let's learn about standard deviation and another measure, which is another measure of variability. So standard deviation is what we're going to talk about today, and it's a measure of variability. So talking about all the data and how much variety there is, how much it differs. I can describe standard deviation as a measure of variability, and I can use technology to compute standard deviation. We're going to try to do all those things today. So let's see how it goes. First of all, what do you notice? What do you wonder? I'm going to use some different colors here real quick just to kind of make sure we're looking at the right stuff. Because I noticed when I looked at this, we have kind of this information here. We have this box of stuff here. So as I'm doing this, you kind of take a look at it all and say, what do you notice? What do you wonder about the information presented in these little diagrams here? They're all different. What kind of things are you noticing between them? Oops, up there. What things are you wondering about? What do you notice? Okay. So we have a wide variety of things going on there. Well, a few things you might notice here with all of them. Well, granted, they're all dot plots, which is a type of way of showing the data. We notice they all have a mean value of 10. Did you notice that? So they all have an average of 10. So if you're to add up all the dots, they all have an average value of 10, which we can see here, here for sure, here, and here. Now, the mean absolute deviation, we've talked about that it's a measurement of looking at the variability within the data spread. We've talked about that being, in a sense, the distance, the average distance, so to speak, from the mean is how you kind of find out what that is. You find the mean, and then find the average, the distance each point is away from that, and then you take kind of the average of those distances. So if the mean in this first one is at 10, the average distance away that the other dots are, or points are from that, is about 1.56. Then it has this new term, a standard deviation of 2, which, if we think about 2, well, if 1.56 is going to be 1.56 is about here away, it's saying that with the MAD, M-A-D, most of the points are in that range right there, right? Standard deviation is saying, well, let's go out 2 points and say most of the points are in this range. So it's a little bit wider of a stretch from the mean, but it does include some more points and does seem to include almost all the points there. When I look at the second one, I have an MADD of 2.22, right? So different from that one, so a little bit larger, right? So 2.22, a little bit larger spread than the 1.56, a little greater. And we can see that indeed the data is more spread out there, right? Makes sense. The standard deviation is 2.58, so it's going to come out to about here, so a little bit further there, but still include a lot of the data points. For the next one, we have a 2.06, which is somewhere between the first and second. So talking about the spread here, 2.06 gets you to here and gets you to here. That does include most of the values. The standard deviation is 2.34, so very similar, a little further out, but not too much more. So it does include them all, but it does pick up most of the dot values there. So there's a lot of similarity between these. We can see that, if the MAD increases like this one, the standard deviation also increases. From here to here, if the MAD score is decreasing, this one's also decreasing. So there's a correlation between the standard deviation and the MAD a little bit there. They're measuring the variability, but in a little bit different ways. When I look over here, I have the mean is there, and a MAD score of 2.68, standard deviation 2.92. A little bit closer together, but still, again, 2.6 away, 6.8, 2.68, 2.92, a little closer to that edge there to include those points. On this one, we have a smaller mean absolute deviation, 1.12. So we would expect with a smaller MAD that most of the values are going to be closer to the mean, which indeed, if you think it's 1.12, that would definitely include most of the values. And standard deviation, same thing, also includes most of the value. So it looks like the smaller our standard deviation and the smaller our mean absolute deviation, the closer most of the values are going to be to the mean. Okay, and let's take a look at the last one. This one has a mean of 10, and it's the mean absolute deviation is 0, standard deviation is 0, which means that, hey, nothing is that is far away from the mean. In fact, we can see they're all exactly the mean. So that's kind of like verifying what we said before is true, that the smaller the mean absolute deviation, the smaller the standard deviation, the closer most of the values are to the mean. Interesting. All right, so these are all measuring variability tools here, whether it be the MAD or the standard deviation. And that's what we're going to be talking about today in today's lesson, standard deviation. So standard deviation, we're going to use technology to find the mean and standard deviation for the data in the dot plots. Partner 1 has this group of dot plots there, and partner 2 has this group of dot plots there. And what we want to do is kind of look at them and use technology to find the mean and standard deviation and see what do we notice about those 2 points, okay? So we have some points here. We have all single points, 1 to 10. We have 10, 20, 50. This one's 5 to 25. The last one is all 2s. These ones are spread. All right, let's take a look here because I went ahead and I put it onto a spreadsheet for us. And so let's take a look here at the first one. So one partner had the points where they had one value of 1, one value of 2, and so on. And when you look at that, when you calculate what the mean is, the mean for that one, oh, I gotta go over here, sorry, wrong numbers. Let's take a look, that's better. One partner had the 1, 2, all the way to 10. The mean in this case was gonna be 5.5 with a standard deviation of 2.87, okay? So this value here, right, we'll call that A, was very similar to partner 2, where they had -9, partner 2, -9 all the way to 0, okay? So this partner had single values in each one of them, but what we can see here is in terms of what the mean is going to be, the mean for this one, we would say let's make it equal to, which you can copy this. I'm going to copy the value, copy and paste. I can see the mean in this case is at -4.3, so right about here between the 5 and the 4. Over here, the mean is between 5 and 6, so that makes sense there. All right, standard deviation does increase a little bit, but they're pretty close to one another there, not too far off. Now the reason for that's probably going to be because we have a value of 0. That's going to change things just a little bit there. I know when I look at my my teacher book there, it shows that they have the same standard deviation, which is interesting. When you do the formula for standard deviation, if you notice, I have to actually look at the bottom left-hand corner. Yeah, it's actually equals, the formula is equals standard deviation, and I want to use a .p. So be careful if you're using a Excel or Google Sheet for that. That's the formula for finding out standard deviation. Then you put your value inside of there. Right, so that's what it's going to look like. And a standard deviation, the .p means it's the whole population, meaning I'm going to include all the numbers, but that's something different. So if you're working with it, you get a different answer, that's probably why. So just be careful about that there. So let's take a look at this one. Did I do standard deviation .p? Yep. So that's what we have there. So those are similar. Again, the mean is 5.5. It says most values here are about 3 away, 2.87, 3 away. Okay. When I look at the average of the ones that are 10, 20, 10, 10, 20, 20, 30, 30, okay, and we find out, okay, what's the average going to be? We're going to do E1 to E10. We get average of about 30, which makes sense because 30 is right about in the middle of things. And so things are going to balance out there. If I want to find a standard deviation .p, and I'll do E1 to E10. I get 14. Now that's a greater standard deviation than I had before, but notice the numbers are also a lot larger too. I'm going from 10 to 50. So I would expect a little bit more of a spread of those numbers there from the center point, the mean. Okay, so let's do the same thing here. I'm going to copy this again, Let's look at when I have 5, 5, 10, 10, 15, 15, 20, 20, 25, 25, the yellow one, which was partner 2. Notice that again, the mean is 15 right in the middle. Deviation is about half of what this one was over here, but again, the values are also about half as well. So that sort of makes sense, doesn't it? When the values are less, then the deviation is going to be less because there's less room for it to move. You wouldn't expect to have a standard deviation of 14 if your middle's at 15, because that would mean that most numbers are 14 less or 14 more. We don't have even 14 more. 14 more than 15 is 29. It's not even a value for us. What would you expect for this next one when you have all these 2's? Well, we would expect that the mean is going to be 2, and the deviation are these numbers moving away from the mean? Well, the answer is no, they're not, right? So we're going to get a standard deviation of 0 in that case, a lot like our first what do you notice, what do you wonder, where everything was at 10. In this last one here, we have a -3, we have 5 -3's, and we have 5 7's. So our mean is going to be in the middle of that, but the mean is going to be something in between 7 and -3, which is just fine. We'll see it's about 2. The deviation, though, is going to be the average distance away. So the average difference away, oh, I got to copy that again. Copy, paste. If the mean is at 2, the average distance away is 5. Well, 2 plus 5 is 7, and 2 minus 5 is -3. So that makes total sense there, that you would have that sort of thing happening. So what we notice about the mean and the standard deviation is we notice in the first plot the standard deviation is the same pretty much because the values are distributed the same way. I think if I was to do this one again, I think I'd change that one. Oh, I see why it's wrong. Watch this. Look at that. This should be a -1. Watch what happens to my standard deviation. It should be equal. Ready? Boom, there it is. I had a typo. That explains the whole thing. So when the numbers are all the same value or distance away from the mean, you end up with the same standard deviation. Just don't make a typo like I did there. All right? In this case here, between the pink and the yellow, we see that, oh, well, the difference here is this is double the value, so I get standard deviation that's about double as well. Here, when there's no deviation happening from the mean, we expect 0. And in this case here, the last one, we see that they're about the same. They are the same distance from the mean, so we get a deviation very consistent, and it's a 5, just like that. Okay? So just some interesting things to look at there when we're talking about mean and standard deviation, for how those things are really working about helping us see the variability of our data. Okay. All right, and the next activity, this is something for you to do. It says to invent some data that fits the conditions. Be prepared to share. So here you have some different conditions that you are going to make some data for, okay? 10 numbers with a standard deviation equal to the standard deviation of your first dot plot with a mean of 6. So this is something you're going to use technology for. I'm not going to do that with you today. And try to figure out number combinations you can use to create something that does that. And you're provided here with 6 different ones that you can do, and I'm going to let you explore those on your own by playing with some numbers and just seeing what happens to your Excel spreadsheets when you do that. Okay, I'm moving over to activity number 3. Again, sometimes I can do most of the lessons, sometimes there's parts that just hard to replicate when it's just you and an iPad. Okay, begin with this data. There it is. We're going to use technology to find the mean, standard deviation, median, and the interquartile range. Remember, interquartile range is Q3 minus Q1 of our box plot. Okay, median is the middle, mean is the average, and standard deviation, we have to use the calculator thing for it. Okay, so we're going to plug these numbers in to find those 4 values. So let's do that real quick because I do have a spreadsheet for that. Okay, so we're going to say check right there, and we're going to pop over here and say check right there, and here we go. All right, so I already had them typed in right there. Those are the values that are in our list, right? 1, 2, all the way to 20. So in this case here, I've already put in the formula for the mean, which is average equals average, and then I did A1 to A20. So we have a mean of 10.5, a median also of 10.5. The standard deviation, I use the formula equals STDEV dot P, and from the values A1 to 20, is 5.76, meaning that most values on average are about 5.76 away from the mean. Okay? The interquartile range, the difference between Q1 and Q3, I wrote those down here just to kind of see what those were. If the median was 10.5, the minimum's at 1, that's our least value. Our maximum's at 20, that's our most value. And then you have to ask yourself kind of what is in between 1 and 10, well, 5.5. And what's between 11 and 20? Well, it's 15.5. So Q1 minus Q3 minus Q1 equals 10. So if we did our box plot, it would look, it'd be a nice little square there. Okay, so what we know so far is that our mean equals 10.5. Our median equals 10.5. Our interquartile range is 10. And our standard deviation is 5.77. Okay? So that's what we know so far. So the next question says, how do the standard deviation and the mean change when you remove the greatest value? How do they change if you add a value to the data set that's twice the greatest value? Okay, so let's first of all remove one, and then let's see what happens. So I'm going to come over here, and you can see I copied it all over for us already in this column here. Same value there. So what happens when we remove the greatest value? Okay, so we'll keep this in mind of what we're looking at here. In fact, let me highlight that for our basics. Okay, we're going to compare everything to those values there. So there's a 20. When I take out the 20, what happens to my values? My mean decreases, which makes sense. I got rid of a high value, so my average will go down a little bit. Standard deviation also decreased, went down a little bit. And the median also went down because I lost a high value there. That makes sense. Now it also then said, well, let's take our high value and double it. So instead of 20, we're going to double it. What do you expect to happen by adding a larger number? Well, when you add a larger value, our mean should increase. Our median should go back to what it was since we're just adding one value, 10.5. But what's going to happen to the new thing, standard deviation? Should it increase if the mean's increasing, or will it stay the same? Well, let's press enter and see. Wow, look at that. The mean went up quite a bit, went up 11.5 from what it was originally, 10.5, all right? But look at that standard deviation. I now have a greater deviation, which means the data is more spread out. It's not as consistent. There is now more variability, is what that high standard deviation number tells me. Wow, that's a big change, isn't it? Okay, the next question then for us to take a look at there, right? We saw this already. We could say we did this one here. When we remove it, everything goes down. When we make it 2 times, everything goes up. Okay, so let's see the next thing. What's going to happen to the standard deviation and mean when you remove the least value from the data set? Okay, so if we remove the 1, we would expect the standard deviation and the mean to actually, since we got rid of a small value, they should increase, right? Let's see if that's the case. Come back over here. So we're going to get rid of the 1. Right now we're at 10.5. So if I get rid of the 1, what happens to the standard deviation and the mean? Yep, it went up, right? From 10.5 to 11, and then from 5.7, now the standard deviation actually went down, which is interesting, right? It went less because it's going to become closer together. I have less of a spread there. So that makes sense because I have less spread happening. So when I got rid of a value, I actually end up with less spread. So let's cross this out. My mean goes up. My standard deviation actually went down because I got rid of the spread. The spread became less, right? And that's what I'm measuring. Okay, interesting. So that's what happens. Our guess was a little off, so we fixed it here. The mean went up, standard deviation went down. What happens to standard deviation mean when you add a value to that data set that's equal to the mean? let's take a look here. Let's come over here. Let's put our 1 back in there, just so we are there. And let's add a value to the data set. I have one over here where I can add a value. I have the space there. So our mean is 10.5, so let's add another 10.5. What happens to the mean and standard deviation? The mean stays the same because we added the same value. The standard deviation actually got a little smaller, meaning that more values are closer to the middle. That makes sense. Okay, so in our case here, we would say that when we do this one here, so the mean stays the same and the standard deviation gets a little bit smaller. What if you add a second value equal the mean? Well, I didn't really set that one up there, so I'd have to actually change some things around. But I would imagine that if we did that there, that's going to stay the same. It's the same value. And our standard deviation will also continue to be smaller because everything's getting closer to the median value. Finally, I want you to add, change from your values and data set to answer the question, what appears to change more easily, the standard deviation or the interquartile range? That would take a little bit of work to do on my spreadsheet. It's not calculating interquartile range on its own. I have to do it by hand. So you'd have to kind of play with it on the app that comes with the program and see what happens there. Okay, but the main thing is we're looking at how that standard deviation is a measurement of variability. So we can describe the variability of a distribution using standard deviation. The standard deviation is a measure of variability that is calculated using a method that is similar to the one used to calculate the mean absolute deviation. A deeper understanding of the importance of standard deviation as a measure of variability will come with a deeper study of statistics, meaning not today. For now, know that standard deviation is mathematically important and will be used as the appropriate measure of variability when mean is an appropriate measure of center. Like mean absolute deviation, the standard deviation is large when the data set is more spread out, and the standard deviation is small when the variability is small. The intuition you gained about mean absolute deviation will also work for standard deviation. So that's kind of the key thing there, right? You're really looking at about the spread and the variability of the data using things like standard deviation or the mean absolute deviation. But we use this one when we have a mean as an appropriate measure of center. All right, here's your cool down for the day that you can definitely work on. And you can read that and do that one. And then we're going to move on over to homework time. As always, make sure you've done it before you start checking your answers. Here we go. The shoe size for all the pairs of shoes in a person's closet are recorded. And we see that they're all the number 7. What is the mean? Well, when everything is exactly the same, the mean's simply going to be 7. Of course, I could do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 70 divided by 10, and I end up with 7. Standard deviation. Well, about how far spread out are all the numbers away from 7? They're not spread out, so our standard deviation is going to be 0. All right, number 2. Which of these is the best estimate or best estimates the standard deviation, the spread of the points in a card game? Looking at this spread, it's a nice bell-shaped curve. It looks like our median is about here, and we'd probably say that our mean is probably about here too. So when you're talking about how spread out the data is the data spread out about 5 points on each side, here to here? Is it spread out 20 points? Well, that'd be 520 or 480. Is it spread out 50 points or 500 points? Which one describes it the best? Probably the 5-point spread makes the most sense. Even though we're not calculating officially, a 5-point spread seems to be a pretty good estimate for a standard deviation for where most of the data are away from the mean. Number 2, refer to the data set. 1, 2, 3, 3, 4, 4, 4, 4, 5, 5, 6, 7. What happens to the mean and standard deviation of the data set when the 7 is changed to a 70? So by doing that, the data got a lot larger, didn't it? Which means that the mean is going to increase. Now, how about our spread of the data? Is it getting closer or further away from the mean? In this case here, the mean value should have been somewhere initially around 4, right? It should have been somewhere around 4. By adding that 70, we know the mean's going to go way up, but also it means that I have this spread. I'm stretching the data out, so standard deviation is also going to increase quite a bit. For the data set with the value 70, why would the median be a better choice for the measure of center? Well, the reason the median is better is because with the data set, we have this skewed data, right? And we're going to say it's skewed right because that 70 pulls the data that way. And because it's pulling it, we're going to get a mean that's much greater than most of the values. Most of the values are here, but I'm going to have a mean that's way over there because of that 70. So a median is going to be a little bit more center and be a better way to measure this data to say where the center's at because of that outlier, because of that extreme number. All right, the mean of a data set A is 43.5 and the MAD is 3.7. And data set B, the mean is 12.8 and the mean absolute deviation is 4.1. Which shows the greater variability? Okay, so to figure that out, we need to look at the MAD score. Okay, the greater the MAD, the more variability there's going to be. So here we have 4.1 and here we have 3.7. So the 4.1 is a greater variability than the 3.7. So set B has the most variability. There's more spread away from the mean. What differences would you expect to see when comparing the dot plots of the two data set? Well, I would expect to see a dot plot here centered around 43.5 and a dot plot there centered around 12.8. I'd also expect to see more of the points in A closer to 43, and with this one, a little more spread out between around 12. All right, number 5, what is interquartile range? That's Q3 minus Q1. Q3 is right here at 14. Q1 is right here at 7. So 14 minus 7, last I checked, was 7. Select all the distribution shapes which mean and median must be approximately the same. Okay, well, when they're bell-shaped, they're going to be about the same. Symmetric, about the same. And uniform, about the same. These ones here are the ones that are a little bit messed up, right? The skewed like that, bimodal like that, not as consistent. So A, D, and E. And number 7, the data represent the number of cans collected by different classes for a service project. Find the mean. So to find the mean, we're going to add all those up. And when we add them all up, we find out that we have 222. We divide that by 12. And when we divide all of that by 12, we're going to end up with a mean of 18.5. Okay, is about our mean there. For the median, I need to put all those in order. Okay, so I have 9, 12, 13, 14, 14, 14, 18, 19, 22, 22, 23, and 42. The middle happens right here between 14 and 18. So the median is going to be 16 right there in the middle. If we eliminate the greatest value 42 from the data set, how does the measure of center change? Okay, so if I get rid of the 42, how do the measures of center change? Well, a couple things. One, we know that I'm getting rid of a large number, so my mean is going to decrease. Secondly, because I'm getting rid of a number this way, I know that my median is going to go backwards one spot. So my median is going to now become whatever's here, which is 14. And the mean, I could take the 222, subtract that 42 value, and now I'm at 180, divide it by 1 less, which is 11, and I get a mean of 16.36. So now my mean has indeed decreased from the 18.5 to 16.36. Okay, so just getting comfortable with data, using it, playing with it. Hope that helps you out, and we'll see you next time for lesson 13. Okay.